Hello class, this is Ms. Friggins with today's video on section 5.3, the logarithmic function. As you're watching the video, please remember to take down important notes, information, statements, formulas. Feel free to pause, rewind, or even replay the video so that you can get a better and clearer understanding. And when you're finished watching the video, don't forget to write down your summary in your notes of the video and then submit the summary as well as a top question via the online WISC before class. All right, let's begin. Now, we have already been talking about logarithmic properties and how they affect exponential functions when we're trying to solve them using algebra. And today we're going to focus on the actual function of the logarithm and see how some important qualities about it, as well as see how it's used in the future. So I'm giving you your summary already. So anyway, so let's take a look at logarithmic function. So let's go ahead and with our graphing calculator, create a graph page. And before we start and start the graph, I want to actually add a slider. And so I'm going to do menu and actions and insert slider all the way at the bottom. I'm going to name my slider B for the base. And I'm going to start my value off at 10 because a common base for logarithms is 10. And of course, I'm going to make my minimum 0.1 because logarithm can't have a base of 0, but it can be every positive number. So I'm going to make my maximum up to 10. And I'm going to change the step size from automatic to, well, I'll leave it at automatic. And I want my slider to be horizontal, not vertical, even though I have that option. So here I have this slider, and I'm going to actually move the slider somewhere over here. And I'm going to now graph that function by hitting tab. And I'm going to type in log. You can type in log, or since I want to vary the base, I'm going to use the log function by that way, or I can hit this button and it will bring up different log. I can go over here and plug in, oh, here it is, log. Okay, two options. So I'm going to put B, and as you see, it's solid because I already have something for B. And I'm going to hit enter. And it's going to give me a graph of the log function. I'm going to change the window because I wanted to show you something interesting about the log function. I'm just going to change the x value to 101. Okay? And I'm going to keep the y value. So what do you notice about this logarithmic function? And I want you to pay attention to it as I change the slider value. So the values of the base I'm going to change. And just take a look at what's going on with the function, what changes and what stays the same. So no matter what I change the base to, certain things still seem to be the case. And what are those things? Well, let's take a look at them one by one. First of all, the domain of the graph is all positive numbers. It never will have a negative x value. So no matter what B is, the domain is always all positive numbers. And the range is actually all numbers. And I know you were saying, no, that can't be because I didn't see it. If you go back over here, you can see that it only stops somewhere over here. Well, actually, that's the limitation of your graphing calculator. It actually approaches this y-axis, but it never stops on the y-axis. And we can figure that out by zooming. And even though it seems to go no higher than 3 here, if I were to continue going on to infinity, eventually the graph will get higher, okay? Another important thing that you should always remember about logarithmic functions is they have an x-intercept at 1, 0. At 1, 0. So whenever I plug in 1 here, I'm always going to get out 0, no matter what B is. And the reason being is the exponential function, if you remember, B raised to any power, B raised to the power of 0 is always going to be equal to 1. So as a result, the logarithmic value, when I input 1 for x, I'm always going to get out 0. And did you notice where the y-intercept was? That's a trick question because a logarithmic function has no y-intercept. It never actually reached the y-axis, even though it looks like it here on this graph. But if I were to zoom in by hitting menu and zoom, well, first I'm going to hit menu and user, and that's going to save my current window. And then I'm going to hit menu, window, and zoom in so we can get a closer look at what's going on over here. And as you can see, the graph never seems to be reaching the y-axis. It just gets really, really close. I'm going to hit menu, zoom. Let's see if it'll go back to my user one like I thought. Oh, no, I think I just changed to that one. But the point is that the graph will never ever reach the y-axis. It will just get really, really close. And that's important to note. So as a result, the graph has no y-intercept at all. And because of that, it also has a vertical asymptote at x equals 0. And in general, no matter what b is, the values of the logarithmic function increase very slowly. We had x all the way out to 100, and the highest the y value reached was like around 2 or 3. Okay, it was no higher than 3. So it increases, but it increases very, very slowly, no matter what b is. So where are logarithmic functions used? Well, we're going to take a look at some examples of that, but before we do, we're going to introduce this new concept called orders of magnitude, which is different from by a factor of, okay? And so an orders of magnitude is only considered when you're comparing different quantities to see how they compare. Sometimes one quantity is a whole lot bigger than the other quantity. And so we kind of get mixed up in all of that. But if we want to actually compute it and compare it numerically, sometimes it can't say, well, it's 1,000 times bigger than it. Although that is descriptive, sometimes they use this concept of orders of magnitude to determine how intense or how much greater the other one is. So in order to figure out the order of magnitude, we do the same thing that we do with any ratio, is we divide them by one by another. But if the result of the division is 10, then it's an order of magnitude of order 1. If the result of the division is 100, then it's an order of magnitude of 2 orders of magnitude. And if the result of the division of the two quantities is 1,000, then it's 3 orders of magnitude. Do you get the trend? So if it was 1,000,000, it would be 6 orders of magnitude. So to figure out the order of magnitude, instead of saying 1,000, we're going to just bring it down to the number 3. Instead of saying, oh, the ratio is 100, we're going to say it has 2 orders of magnitude. And you can do that by dividing the two quantities and then taking the log of them. And so the log of 100 is 2, the log of 1,000 is 3, and vice versa. And that occurs when, and let's add another page so you can see that. So if I were to go ahead and just type log of 1,000, I'm going to get 3, okay? So let's compare that. Let's compare 1,000 won to 1 won. Oh, you guys already know what that is. But let's just compare 1,000 divided by 1. And I get 3. And because that's the log of 1,000 divided by 1, then we would say it's 3 orders of magnitude. The log of 1,000,000 divided by 1 is 6 orders of magnitude. Okay? So it's just another way to compare ratios. To compare quantities where they're by ratio, but the values are really, really big. Their ratio is really, really big. Okay? And so that's important to note. If you need to write down anything, I would definitely write down this formula as well. And this is what it means. As you can see here, this box is 1,000 times as big as the first box, but we don't want to say 1,000. We can say it's 1,000 times bigger, but we'll say is that this box is 3 orders of magnitude bigger than this box. Just a different way of saying it. So where are functions, logarithmic functions, used in real life situations? We're going to take a look at 3 examples. In chemistry and acidity, gosh, I can't pronounce stuff. and this is with pH levels. Our bodies are should be more basic. I don't know, I'm not a chemist, but we have a pH level of 7 to 14, and the way you compute that is by where H represents the concentration of hydrogen in the blood, and you take the negative log of that. So sometimes we have a whole lot of hydrogen concentration in our blood. Or maybe it's very small. No, it's very, very small. The amount of, anyway, sorry, getting all distracted. I am not a chemist, so I don't have a good hold of describing chemistry related things. The second thing is geology, the Richter scale. If you remember, everyone knows about the earthquake in Nepal, and they said it was a 7.9 on the Richter scale. And for us, that's really huge because you compute that number by taking the log of the difference of the ratio of two quantities, the intensity of the earthquake divided by just the regular intensity of everyday vibrations of the earth. And if it was a 7.9, that meant that it was at least almost 8 orders of magnitude larger than a regular day. That was the intensity of the earthquake. So we're talking about if that was close to 8, that's like 10 to the 8, which is like almost a billion. Actually, it's like 100 million, orders of 100 million ratio between the two. Sad. And then also with sound, when you turn your volume up, you're changing the decibel level, and the decimal level is based off a logarithmic function between a ratio between I, which is the intensity of sound you want, divided by, now in this example, it says 10 to the negative 12, where that represents the intensity of sound at the softest that a human ear can hear. Your book says it's 10 to the negative 16. You could also just take a look in this and say, well, this is just I naught, where I naught represents the smallest you can hear, the human ear can hear. That might be better for you to understand. Okay. All right. A couple more things before we leave. I wish I had more time to do examples, but the examples are going to be in the book, or very helpful, so please look at the book. We want to talk about asymptotes because even though they talk about it briefly in this section, it will be very important for all of your, for future sections in Precalculus. So it's good that you know the difference between asymptotes and what asymptotes are and how they're related to describing a limit. So horizontal asymptote is basically a horizontal line at some point A where the graph does not cross that line. And so we can describe it as saying, as x approaches infinity, f of x is going to be, the limit is going to be equal to A from both sides. And the way you can describe it, and sometimes logarithmic graphs are confusing because it looks like it has a horizontal asymptote. But if the graph does like this, then that means it has some type of horizontal asymptote at some A value, okay? Now, if the graph crosses this line, then this line can't be an asymptote, okay? So that's an example of a horizontal asymptote. A vertical asymptote is what we saw with logarithms. The graph will not cross the vertical axis. And I wanted to point out two things. Let's say I have two graphs. Here's one graph and here's the another graph. They both have the exact same horizontal asymptote. This graph will never cross below the line, and this graph will never cross above the line, okay? So the limit for both of these functions as x approaches infinity and negative infinity would be either A, well, not and, let me clarify. The limit as x approaches infinity of f of x is A. The limit as x approaches negative infinity of this graph is not going to be A because it's going far away from the graph. It probably is infinity. And the same occurs for a vertical asymptote, but like I said, for the vertical asymptote, and let me put the line here. If I were to continue drawing this so that this one would do something like this, then the y value is going to infinity. Okay, or if it's in this case, the y value here for logarithmic functions is going to negative infinity. Okay. The difference between these two is the infinity. And the difference between horizontal and vertical is that vertical asymptotes always have as their limits either infinity or negative infinity. And horizontal asymptotes always has as their limit a number that is not infinity or negative infinity. Okay? Even though, and if you take a look at what they're approaching, in this case, the x's are always approaching infinity or negative infinity for a horizontal asymptote. Oops, wrong color. But for a vertical asymptote, the x's are always approaching a number that's not necessarily infinity or negative infinity. Okay, this video is a lot longer than I planned, but I wanted to be very descriptive, and it covers a lot of good information. All right, see you tomorrow.